Hello, this is Lazarus at telecomTech, where telecom and networking technologies are simply explained. Today we'll be simply explaining how a network switch works. For most people who are not very well informed about networking, they buy a switch, connect all their hosts and devices, as well as their connection to the internet, and they're all up and running. All devices can talk to each other, and they can reach the internet, and they're happy. Yay! But there's so much more happening under the hood that is very important as far as switching goes. And it's all the more important to understand this when you deploy larger, more complex networks, as well as when you're troubleshooting. Understanding is key to performing your job, but it's also key to getting certifications that are based on these topics. And for this reason, we'll dig deeper in this video to find out more about how switches work. A switch is a device that has many ports, and typically these are RJ45 ports for use with what are typically called Ethernet cables. A switch may also have one or more other types of ports. Typically these are SFP ports, which can accept a transceiver that is able to connect various types of fiber optic cables. In any case, the important thing here is that a switch has many ports. I've seen switches with 4, 5, 8, 12, 16, 24, 48, 96, and even more ports, especially for those switch models that are modular and can have multiple line cards added to them. So at the upper end of the spectrum, you may have a switch with hundreds of ports. So since a switch has many ports, it's designed to connect multiple devices and typically end devices such as PCs, laptops, IP phones, IP cameras, printers, TVs, wireless access points, and many others. Switches don't always connect end devices, but usually. We'll see this in detail later on. Before we take a look at the actual operation of the switch, let me tell you a bit more about the MAC address table. This is a construct that's created within the memory of the switch, which corresponds MAC addresses to ports. And based on this MAC address table, the destination MAC address of an incoming frame is examined, and the frame is sent out of the corresponding port as shown in the MAC address table. This table is initially empty, but it becomes populated as frames begin to be sent. This is how a switch performs switching at its most fundamental level. So if you have a switch and you connect, say, 4 devices to it, each device now has an active connection to that switch. Whenever data is sent from a host, it is encapsulated and specific MAC addresses are assigned to the frame. Specifically, we have the source address, which is the MAC address of the sending host, and the destination address, which is the MAC address of the intended destination. Now on this diagram, I have very short MAC addresses just for convenience. They're not that small in actuality. We'll see what they actually look like. But for now, in the diagram, it just helps to keep them short. Now let's say that we've just turned on our switch and our MAC address table is empty. There's a communication between host A and host B. So host A prepares the data, encapsulates it, and it reaches the data link layer, or layer 2, in that encapsulation process. It places an Ethernet header in front with the source address and the destination address and sends it to the switch. As soon as the switch receives it, it reads the source and destination MAC addresses, and it does 2 things. First of all, it populates its MAC address table with the source address and corresponds it to the specific port on which the frame came into the switch. Since the source address came in on that port, that MAC address lives there and can be reached via that port. Then it looks up the destination MAC address in the same MAC address table, looking for the corresponding exit interface that it should send that frame out of. But initially, the MAC address table is empty, so it will flood the frame out of all ports except from the one it was received on. All hosts will receive this frame. They all decapsulate it up to layer 2 and examine the destination MAC address, and if it's not for them, they simply discard it. If it is for them, and that's the case for host B, the frame is received, decapsulated further, and processed. Now, this whole process has allowed us to complete the sending of the frame, but it has also served the purpose of populating the MAC address table. Now, when host B wants to respond, it will do the same thing. It sends its frame with a source MAC address of its own and a destination MAC address of host A. In this case, the MAC address table will be populated with host B's MAC address and its corresponding port. Then the destination MAC address is looked up in the MAC address table, and lo and behold, we see that there is an entry along with its corresponding exit interface. So since we know where host A's MAC address lives, the switch sends that frame out of only that port. Host A receives the frame, examines the destination MAC address, sees that it belongs to itself, and it decapsulates and processes it. Now, the magic is in this MAC address table. It allows the switch to perform switching. It allows the switch to take a frame, know where it has to switch it to, and send it out of the corresponding port without the need to broadcast every single frame that comes in to the switch. So through this whole process, the MAC address table is populated, and all subsequent communication can take place directly between the intended hosts rather than out of all ports. And this is a very important part of what switches have to offer, as they make communication much more efficient in this way. Now, because Layer 2 deals with communication from hop to hop rather than from end to end, the destination MAC address in any such communication should be that of either the destination host or that of the very next routing device, like your default gateway. The destination MAC will be that of a host if the destination of the communication resides on the same network segment. If, however, the destination resides on a different network segment, like this host Z here, then the destination MAC address of the very next hop from host A will be that of the default gateway, which has a MAC address of DD in this case. In that event, Layer 2 mechanisms will ensure that the frame gets its payload to the very next hop. Now, once there, the same process takes place again as the frame is sent out of the interface of the router to get to the next router. The source and destination MAC addresses are those of the sending and receiving routers. This continues from hop to hop until the final hop that takes place gets the payload to the destination host. So that, my friends, is an overview of switching, how Layer 2 MAC addresses are placed within the header of an Ethernet frame, and how these addresses are used by switches to get that payload to the intended destination. And it's also how Layer 2 is involved in getting data from hop to hop, from routing device to routing device, until it gets to the destination. Now, I know that this is still a bit superficial. This is still a high-level overview. We're going to be drilling down more deeply into all of the various related technologies and concepts. So stay tuned to future videos. That, my friends, was an overview of Layer 2 and how a switch performs its function. Well, if you've watched to this point of the video, then you're probably one of my more faithful followers, and I appreciate that. I'd just like to share with you my recent publishing of content on my website at www.telecomTech.io, where you can find more in-depth courses on networking topics with labs, quizzes, exams, and in-depth configurations. I don't yet have very many courses available, but more are coming soon. So check it out, subscribe to my newsletter, and get better deals on the courses as I publish. I'm Lazarus at telecomTech. I hope this has been helpful for you, and I'd like to thank you for watching.